it's basically based on the conflict estimation algorithm. But the conflict estimation algorithm, we have to prepare some good wave function, approximate wave function, which have the large overlap with the target electron state. So the big problem, big question is how to prepare such a correlated wave function on a quantum computer. So today I'm going to talk about this point. So but let me start with the same slide as the previous talk. So basically, in the fundamental calculation, we solve the Schrodinger equation, that is a fundamental equation, to treat the to theoretically reveal the electron structure of a molecule. So we usually use a von Oppenheimer approximation, in which the atomic special calculation coordinate for atomic signal is fixed. So in this case, so we can calculate the energy and wave function of the molecule as using the input as using atomic quantity of the molecule as an input. Of course, calculating this Schrodinger equation is very difficult. I mean, the exact calculation of Schrodinger equation is very usually impossible. So we have to introduce some approximation. But if we can calculate the electron state very accurately, we can search, for instance, search for the stable transformations, or we can calculate the maximum molecular properties, or we can calculate the reaction pathways. So basically, if we can accurately calculate, perform the quantum chemical calculation, it potentially opens a door to in critical quantum chemistry research and development. And this is the Schrodinger equation, Hamiltonian, electronic Hamiltonian, under the von Oppenheimer approximation. We have kinetic energy for the electron, electron nuclear interaction, and electron interaction term. But solving this equation exactly is very difficult, and you can see the Paul stated that in 1929, the underlying physical rules for the mathematical theory of a large part of physics and the whole of chemistry are completely known. But the difficulty is that the exact application of these rules leads to the equation much too complicated to be solved. But if we can use the quantum computer, we can solve this kind of problem much more efficiently because we in quantum chemical calculation we create a motion of electrons in the molecule, and electrons are quantum mechanical particles. So such quantum dynamics of quantum mechanical particles can be simulated very efficiently by using a computer itself built of quantum mechanical element, which means that the quantum computer. And we have a quantum algorithm, which was first developed by Alan Sugisaki in 2005. By using this kind of approach, the calculation of time for the energy of atom molecule scale exponentially with the system size on a classical computer. This means that the full CI on a classical computer scale exponentially with the system size, but it becomes polynomially using a quantum algorithm. And there are two major quantum algorithms for quantum chemistry. One is the quantum phase estimation, and another one is the variation from eigensuper VQE. QPE is the full, basically we compute the electron state fluid quantum except for preposition. The idea is, I will explain in the next slide, but anyway, the idea is we perform the time evolution of the Hamilton of wave function under the Hamiltonian to extract the eigenenergy E as a phase in the wave function. And this approach, we can obtain the full CI or cut CI wave function, and we can obtain the eigenenergy. But the quantum study is usually very deep because we have to simulate the time evolution of the under the Hamiltonian, which causes many. So it means that the time evolution operator include, roughly speaking, all the n to the fourth power of the term, And because Hamiltonian include many terms, we does not commute to each other. So we have to apply total composition to simulate that kind of vision. So the quantity is usually very deep. So usually applying this QPE to the hardware currently available is very, very difficult. If we can use if we use VQE, in the VQE, this is basically a quantum cluster hybrid algorithm. So the basic idea is very simple. First, we perform some unit operation to some initial state, which correspond to the wave function, and we can calculate the energy excitation value by using just the equation. And because there is a variation principle, we can optimize this data to minimize the total energy. Using this approach, we can obtain some unit coupled cluster or some heuristic wave functions, and we can obtain the energy excitation value. The big difference is the depth of the quantity, because in VQE, only we have to do is generate some approximate wave function. So usually this U theta is much more shallower than the time evolution operator. So the quantity required for VQE is much more shallower compared with the QPE. But today focus is the QPE part. So basic idea of quantum field expansion is assume that we have a wave function psi. And if we apply a time evolution operator, and if this wave function psi is an eigenfunction of the Hamiltonian, application of this time evolution operator doesn't change the shape of the wave function. And the difference appears only the phase. And the phase shift depends on the energy, E. So if we can determine the magnitude of phase shift caused by the time evolution, we can extract the eigenenergy by using this equation. So this is the basic idea of quantum phase expansion algorithm. And what we usually do is QPE with n of unshared qubit. So here we have some unshared qubit here, and we have additional some qubit which is used to store the wave function. In this case, first we apply Agama gate to unshared qubit to generate the equal superposition on state. After that, we apply control unit operation. Here, U is the time evolution operator, and then perform the inverse QFT. And finally, if we measure the quantum state, we can obtain some bit string. And the bit string corresponds to the digit of the eigenphase phi. So if once we obtain this eigenphase phi, we can easily calculate the energy by using this equation. But the problem is we want to calculate the wave function, because in quantum chemical calculation, we want to obtain the wave function and energy. But in QPE, we need a wave function as an input. So usually preparing the exact wave function in the beginning on QPE is impossible. I mean that if you already have the exact wave function, we don't have to calculate the QPE, perform the quantum chemical calculation at all, because we already know the answer. So we have to use some approximate wave function. And if we use an approximate wave function in the QPE, so in this case, I wrote the approximate wave function at phi, which can be expanded by a linear information on eigenfunction. If we use this kind of approximate wave function, this quantum study transforms the quantum state to this state. So it means that if we measure the quantum state qubit, we can obtain one eigenphase of the Hamiltonian, and the state is projected onto the corresponding eigenfunction. But the probability to obtain one particular eigenstate is proportional to the question Ck. Is actually the square of the question Ck. So it means that let us think about the situation that we want to calculate the ground state. If the square overlap of the approximate wave function with the first wave function of the ground state is exponentially small, it means that we have to perform the QPE exponential number of exponential times to obtain the ground state energy. So it means that basically the QPE can be done in a polynomial time. So basically, if we use the QPE, we can obtain the eigenvalue, one eigenvalue or corresponding eigenfunction in polynomial time. So it means that, roughly speaking, we can obtain some exponential acceleration from the classical computation. But if the overlap is exponentially small, we need exponential number of QPE experiment. So which probably the advantage of the quantum figure. So we have to develop some quantum algorithm or some quantum technique to generate some correlated wave function, rather overlap with the exact ground state, starting from some approximate, very close approximate wave function with some shallow quantum study. Actually, this problem is very difficult. I mean that this is known as the wave function overlap catastrophe. And this is a very famous paper published from written by Garnet Chang. In this paper, they claim that the availability of exponential quantum advantage can center on the regular feature of the physical problem that enable efficient heuristic quantum state preparation, also enable efficient solution of classical heuristics. So roughly speaking, in order to accelerate the quantum chemical calculation using QPE, we have to generate some approximate wave function using quantum heuristic in polynomial time. But if the same state can be prepared in classical computer in polynomial time, it means that it is quite difficult to verify the quantum advantage. And they claim that we conclude that the evidence for such an exponential advantage across chemical space has yet to be found. So roughly speaking, if we can generate some approximate wave function on classical quantum computer in efficient way, we can also generate the approximate wave function on a classical computer in efficient way. So most of the textbook for quantum chemistry on quantum computer, we usually use the Hartree-Fock wave function as an input for QPE. But is the Hartree-Fock suitable for the initial wave function in QPE or not? Actually, Hartree-Fock is acceptable only for small weakly correlated modes. You can easily assume that if the system molecule is strongly correlated, it means that the wave function is well approximate. It's not approximate by a single configuration, and we have to take into account many configurations to simulate, to mimic the wave function. But additional condition we have, the molecule should be small enough. Why? Because there is a sigma overlap decay exponential with the sigma size. So we can easily understand this. So let us assume that we have we want to calculate a water molecule. Water molecule is a typical system of which wave function, Fourier wave function, can be well approximated by a Hartree-Fock configuration. The Hartree-Fock configuration for the Fourier of the Fourier wave function of the water molecule is about this CHF is, of course, rather than 0.9. But let's think about we want to calculate the hydrogen water molecule dimer. Of course, the wave function for this water molecule B can also be written like this. And in the extreme limit of weak interaction case, this water molecule dimer or wave function of the water molecule dimer can be written like this. Now the Hartree-Fock configuration, the contribution of Hartree-Fock configuration appears in the first line. And the question for the Hartree-Fock configuration is CHF times DHF. So roughly speaking, if CHF equal DHF equal to 0.9, the Hartree-Fock configuration for the water molecule dimer is become 0.9 is 0.81. If we have 10 10 water molecule clusters, you can easily assume that this Hartree-Fock configuration becomes 0.9 times to the 10th power. So we can easily expect that the overlap with the Fourier wave function decay exponentially with the number of water molecules. Okay, so it means that Hartree-Fock can be used as an initial wave function in the QPE only for small molecules, small and weakly correlated molecules. So in order to apply the quantum phase estimation algorithm for large molecules, in the extreme case like proteins, it is quite difficult to obtain the quantum phase energy using Hartree-Fock wave function as an initial wave function. And this is an example of strongly correlated system. I mean that even for very small molecules, the Hartree-Fock wave function is a good approximation around equivalence of. As you can see, this is a potential energy curve for the hydrogen molecule. And this is the energy. This is the blue one is the Fourier I, and red one is the Hartree-Fock energy. Right-hand side is the overlap with the ground between the Hartree-Fock wave function and the Fourier wave function for the ground state. So as you can see, the overlap with the Fourier wave function is close to 1 around the equivalence energy. But if we elongate the bond distance, the overlap becomes close to 0.5. So roughly speaking, molecules undergoing bond extension are dangerously open shell systems, which so open shell systems are basically a strongly correlated system. And this kind of open shell systems are not just a reactive intermediate, but unusual molecules, but fundamental in chemical species. So there are many open shell molecules, like this is a mangan from clusters, which is used as a spin cubic molecule. Actually, this molecule has a spin doublet branch state s equal 1/2. So this molecule can be used as a cubic because spin 1/2 system has 2 sublevels, I mean upspin and downspin. And also molecular covalent dissociation, covalent bond dissociation generates some bilateral states. There are many this kind of nuclear control metals which have open shell characters, and they are very important in the biosector. and also some materials like nanograpphene, we have some opposition character in the zigzag edge level. And this kind of stuff, biological, can be used as some electron transmitter or something, conductor. So this kind of biological has been extensively studied experimentally. But in this model, each radical has unpaired electron. So if we this biological stuff, there are many electrons. And also, before studying about the construction of this kind of correlated wave function, first I would like to talk something about the wave function representation in the local and local object, because the wave function representation depends on the object being used. So let us think about just simple hydrogen molecule in the bond dissociation area. We can use, for instance, the local orbital, or we can use local orbital. So this is a typical Hartree-Fock orbitals, but we can use this kind of local orbital. So in this case, approximate wave function for the lowest single state in the bond dissociation limit is become something like this. So in the local orbital basis, the singular wave function is a linear combination of that be occupied, unoccupied, and unoccupied, doubly occupied configuration. So here I label the phi s because this is symmetric and this is asymmetric. So it's phi s and phi a. And here we have phi l and phi r. In the local basis, the single wave function can be written as alpha beta minus beta alpha. Okay, W occupied, unoccupied, minus unoccupied W occupied. Alpha beta minus beta alpha. The representation depends on the orbitals. So we have to take care about which orbital is used in the approximation, in the wave function expansion. So here I will talk about in the local orbital base. So by using local orbital base, how to generate the spin eigenfunction of which is a good approximation for the optional molecules. So the idea was, the paper was published about 8 years ago, but actually this study started from 2013 or 2012. So I need more than 3 years to publish this paper, actually. But anyway, let us think about the hydrogen cluster with 5 hydrogen atoms. Because there are antiferromagnetic interaction between near-neighbor hydrogen atoms, expected spin configuration is become something like this: up, down, up, down, up. And if we use the local orbital basis, and in the orbital local to each hydrogen atom, we can expect that the wave function can be approximated by alpha, beta, alpha, beta, alpha configuration. But if we use this determinant, one single determinant wave function in the Kroner phase estimation, what we expect, what we obtain is something like this. So in this case, this horizontal axis is the full scale energy, and vertical axis is the overlap with the full scale determinant. So this is the ground state we want to calculate. If we use this determinant as an input of QPE, the probability to obtain the ground state is just 0.227. And actually, the aesthetic state S equals 1 S state has larger probability than a ground state. Why? This is because the wave function, full scale wave function, can be, if we calculate the Fuchs wave function for this system, we can obtain this wave function. So you can see, we approximate Fuchs wave function using this, the first term. But we have another 3 terms having almost equivalent amplitude as the first term. And this is because the wave function is a simultaneous eigenfunction of the Hamiltonian and S-square operator. Unfortunately, this single determinant is not an eigenfunction of the S-square operator. Roughly speaking, this is the reason why we obtain very small probability to obtain a ground state. And if because this is not an eigenfunction of S-square operators, even we want to calculate double ground state, but we can some probability to obtain some other spin state like 3/2 and 5/2. This is because this is not an eigenfunction of the S-square operator. So basically, in order to make the probability of obtaining ground state much more higher, we have to generate the spin eigenfunction. I mean, the eigenfunction of the S-square operator by taking some linear combination of Schrödinger determinant. And this is a basic idea. And if we use the spin symmetric adapted wave function known as the configuration wave function, which is written like a linear combination of these 4 Schrödinger determinants, we can obtain the probability. We can obtain the ground state with the probability about 0.881. So roughly speaking, the probability of obtaining the ground state using the single determinant is just a 0.22. But if we use the configuration function, the probability of obtaining the ground state becomes about 4 times larger because we include 4 different Schrödinger determinants. On how to generate this kind of spin eigenfunction? This kind of spin eigenfunction or n-spin system can be generated by adding 1 electron spin to the spin eigenfunction of n-1 spin system. Actually, this kind, so we can obtain this recurrent formula by applying based on the addition theorem of the angular momentum. We can derive these 4 equations. And because this is a recurrent formula, so this is the spin eigenfunction of the n-spin system in the left-hand side. We have spin eigenfunction of n-1 and 1 spin system in the right-hand side. We already know the spin eigenfunction of the 1 spin system is, I mean, the spin eigenfunction for the 1 electron spin is just alpha or beta. So in order to generate the spin eigenfunction for 2 spin systems, we can use spin eigenfunction for 1 spin system here, and we just add spin alpha or spin beta. So basically, we can generate arbitrary spin eigenfunctions or arbitrary number of spins with arbitrary spin point number and also MS value. And roughly speaking, the configuration function have different spin configuration, but this different spin configuration can be constructed by using this kind of known as a branching diagram. So different spin configuration can be expressed by different root in this branching diagram. For instance, if we want to calculate the spin doublet state for 5 spins, we have 5 different pathways to arrive this state. And basically, we can generate the spin eigenfunction of 1 spin system using this kind of And the number in the circle represents the number of possible pathways to arrive at this point. But anyway, we can use this kind of approach. Basically, we can first in order to calculate the generate the spin eigenfunction, first we specify this kind of spin configuration. After that, we can apply this recurrent formula to obtain the corresponding spin eigenfunction. And using this kind of approach, basically we can generate arbitrary spin eigenfunction for arbitrary spin system. And this is a local orbital basis, called local orbital basis. But unfortunately, this kind of spin configuration scale function is a good approximation for long dissociation limit. So roughly speaking, the Hartree-Fock wave function is very suitable, have large overlap with the full-scale wave function in the vicinity of the equilibrium zone. So actually, you can see that this plot, this purple plot, specifies square overlap with the full-scale wave function for the Hartree-Fock scale. The Hartree-Fock scale have large overlap with in the vicinity of the equilibrium zone. But the overlap becomes smaller if the bond dissociates. But in contrast, if we use the configuration function, which is an eigenfunction I talked before, this configuration function is a good approximation for bond dissociation limit. But approximation becomes worse if the geometry close to the equilibrium zone. So it means that here we can use the Hartree-Fock scale as an input for QPE. In this region, we can use the configuration function. So how about somewhere in between? So in this paper, I described how to generate the good initial wave function for QPE in this region. So basic idea is the construction of multi-configuration wave function. So roughly speaking, Hartree-Fock is a single configuration. And this one, I consider only single configuration function. In the vicinity, somewhere in between, we have to consider more than one Hartree-Fock determinant, I mean the spherical determinant, or more than one configuration function. So in the local orbital basis, this is the potential curve for hydrogen molecule. In the local orbital basis, the ground state in the vicinity of the equilibrium geometry is approximated by the Hartree-Fock configuration, W occupied, unoccupied. But in the bond dissociation limit, the wave function can be approximated by two configurations, W occupied, unoccupied, unoccupied, W occupied. Somewhere in between, the wave function can be approximated like this: W occupied, unoccupied, unoccupied, W occupied. But with unequal question. So the problem is how to evaluate this question without performing the CI calculation, for instance. Because we want to prepare the wave function without performing any post-Hartree-Fock calculation, because post-Hartree-Fock calculation have some more complication cost. So it is very hopeful if we can generate this kind of much configuration wave function only performing a Hartree-Fock calculation. Okay, so basically, the wave function of this kind of tensor graph of the wave function can be written like this. And here, y is equal as a directional character, which is a measure of object electronic configuration. So roughly speaking, in the Hardy-Fock case is y equals 0. And bone dissociation limit, we have y equals 1. Somewhere in between, we have a hierarchical character, something in between 0 and 1. And actually, this hierarchical character can be calculated by using the occupation number of the lower unoccupied natural orbital. The natural orbitals are eigenfunctions of the density matrix, one-body density matrix. So, roughly speaking, you can obtain the natural orbital by diagonalizing the density matrix. Usually, Hardy-Fock orbitals are eigenfunctions of the Fock operator, which returns the orbital energy as an eigenvalue. But we can diagonalize the one-body density matrix to obtain the natural orbital, which returns the occupation number as an eigenvalue. If once we obtain the occupation number, we can substitute occupation number for the lowest unoccupied natural orbital to obtain this hierarchical character. So what we need is just perform the Hardy-Fock calculation, but not usual Hardy-Fock, because conventional Hardy-Fock becomes just this configuration. So it means that every orbital are either doubly occupied or unoccupied. So it means that the Hardy-Fock orbitals are actually eigenfunction of the density operator. So well, so roughly speaking, the Hardy-Fock orbital is already diagonal in the density matrix, and the eigenvalue are either 2 or 0. So in this case, we have to perform some open shell and use unrestricted Hardy-Fock calculation. So actually, what we do is calculating the so-called broken symmetry wave function, like this configuration. And we can obtain some open shell wave function and then diagonalize the one-body density matrix to obtain the natural orbital. Then we can calculate the hierarchical character y, and then we can construct a multi-configured wave function in the natural orbital base. So the conventional wave function is something like this, but in order to calculate the hierarchical character, we calculate the Hardy-Fock calculation using this broken symmetry wave function, using a local orbital, one spin put on the left-hand side, another spin on the right-hand side. So basically, using local molecular orbitals breaks spatial symmetry, right? Because in the right-hand side, the left-hand side, the Hardy-Fock orbital has symmetry or anti-symmetry. So they have clearly a kind of symmetry, right? But here, because we localize the orbital, so some spatial symmetry is already broken down. And also, this broken symmetry wave function is not an eigenfunction of X-square operator. In fact, this wave function is written as a linear combination of spin singlet and triple scale. And if you calculate the equation value of X-square operator, you can obtain the equation value equal S-square of equation value to be 1. So roughly speaking, this broken symmetry wave function breaks spatial symmetry and spin symmetry. But we can enhance the wave function representability by breaking this spatial and spin symmetry. if we use this program wave function, we can obtain some fraction of Cation number in the natural object base, which can be used to calculate this diagonal character. Actually, this BS-US broken symmetry wave function can describe bond diffusion limit correctly. This is because, roughly speaking, this broken symmetry wave function is a linear combination of open shell singlet configuration and open shell triplet configuration. And in the bond diffusion limit, there is a exchange interaction between spin, but the exchange interaction becomes small in the bond diffusion limit, becomes zero in the bond diffusion limit. So the singlet state and triplet state become degenerate. So this is the reason why this broken symmetry has a fork with the energy very close to the frequency I. But this broken symmetry wave function is not an eigenfunction of extra operator. So this is a mixture of spin singlet and triplet states. But anyway, once we calculate the diagonal character, we can easily generate a two configuration wave function by using this formula. Here we have two. This is an example for hydrogen molecule with HO3G basic set. First, we have to generate the Hardy-Fock configuration by applying two NOT gate. Okay, we can apply this for gate to generate two configuration wave functions. And the rotation angle theta can be calculated using this equation. And if we use the two configuration wave function, the overlap with the flux wave function becomes something like this solid line. In the vicinity of the equilibrium geometry, broken symmetry Hardy-Fock converges to the conventional Hardy-Fock, traditional Hardy-Fock case. So this is the reason why the Hardy-Fock line and the BS-US line overlap. So this is just we use the in the BS-US broken symmetry UHF, we use this configuration as an input, initial guess of the Hardy-Fock case. But if this configuration is energetically much more higher than this configuration, in that case, the HF cycle converges to this state. So this is the reason why BS-US line and Hardy-Fock line overlap here, and we can obtain the overlap value, equivalent overlap value for Hardy-Fock and BS-US value. But anyway, important thing is by using this kind of wave function, much configuration wave function, we can generate the approaching wave function having much more larger overlap with the exact ground state than the Hardy-Fock single configuration wave function. Okay, so basically there are many approaches to construct approaching wave function. So first, I talk about the configuration wave function. The functionality to prepare configuration wave function is usually very shallow. But the wave function obtained from using this approach is non-variable. Unfortunately, this configuration wave function does not include dynamic correlation effect. So if we expand the system to 5 hydrogen system to 9 or 11, 13, the success probability of QPE becomes something like this. If we use the single determinant, the success probability decay exponentially. But even if we use the configuration wave function, the success probability decay linearly. So we can easily expect that applying this approach to, let's say, 100 of hydrogen atom clusters, it is very the overlap with the Fourier wave function becomes very small. Another approach I took was much confusion wave function. Again, this much confusion wave function is non-variation function. Unfortunately, this wave function doesn't include dynamic variation. So basically, the overlap with the economic wave function becomes smaller for larger system. Another possible approach is, of course, VQE. Because VQE variation approach, it can give accurate energy and wave function even for large system if the approximate answer is selected. But for large system, the measurement and optimization cost becomes significant. So it is quite difficult to apply VQE for very large system. So can we generate the accurate wave function or approximate wave function with polynomial cost of finite number or maybe no measurement? It is quite valuable, I think. So in order to do this kind of thing, we focus on the adiabatic Kupanga algorithm. So roughly, here I would like to briefly explain the adiabatic Kupanga computing. So we focus on some time-dependent Hamiltonian with looking at the linear combination initial Hamiltonian and final Hamiltonian. And that this expansive T is a Friesian function which up from 0 in the beginning of the time evolution and becomes 1 in the end of the time evolution. So if T equals 0, this Friesian function is 0, so it means that the starting Hamiltonian is just the initial Hamiltonian. And in the end of the time evolution, we have the Friesian function if T equal to 1, so it means that the final we have final Hamiltonian in the end of time evolution. This initial Hamiltonian and final Hamiltonian should not commute to each other. Otherwise, if two Hamiltonians commute to each other, it means that they have simultaneous eigenfunctions. So it means that even if we use this kind of time-dependent Hamiltonian, the wave function doesn't change. So they should be uncommon to each other. And eigenfunction, especially the wave function of this H init should be prepared very easily. And if we start from the eigenfunction of initial Hamiltonian and change the Friesian function slowly, we can obtain the in the end of the time evolution, we can obtain the ground state wave function of the final Hamiltonian. So basically, if the variation of the Hamiltonian, time-dependent Hamiltonian, HT is so enough, we can obtain the ground state at t equals small t equals large t. If we change the Hamiltonian very rapidly, there are some there are some transition occurs from the ground state to ecstatic state. So if we sweep the wave function Hamiltonian very fast, we can obtain not only the ground state, but the obtained wave function can be obtained wave function can be contaminated by the ecstatic state. So how to set the evolution time is very important. But there is a known some approximate equation. So roughly speaking, the evolution time t should be sufficiently larger than this value. So roughly speaking, the evolution time should be sufficiently larger than the inverse of the square of the energy difference between the one static state. And this term represents the probability to transit to other state. But this equation is approximate in the sense that it doesn't result in the strict inequality. So in order to apply this kind of approach to wave function preparation in quantum chemistry, we can start from the Hartree-Fock wave function, and because Hartree-Fock wave function is an eigenfunction of the Fock operator, we can use the Fock operator as a starting wave function, starting Hamiltonian. And we can use the full Hamiltonian as a final Hamiltonian. But in order to simulate this kind of adiabatic quantum computer in the gauge-based model, first, we have to discretize the time evolution step and perform the time quantum simulation for the time-independent Hamiltonian at each step. But the Hamiltonian should be defined at each step. So what we want to simulate is something like schedule function is something like this, just linear line. But in the gauge base, we have to discretize this line and approximate by this kind of steps. An important thing is that in adiabatic state preparation, we can obtain the correlated wave function as an output without performing any quantum measurement. So it means that in the case of VQE, we can check if the wave function is closer to the exact wave function or not by calculating the total energies. Because there is a variation principle, lower energy means that the wave function is more accurate. But this adiabatic state preparation, we don't measure the quantum state, so we have to set the appropriate computation condition in the beginning of the computation. And we cannot verify if we cannot check the wave function during the computation. So we have to know what is the type of the source of error. So there are several types of source of error. One is the non-adiabatic error, which means that this large K is too short to follow adiabatic. Another source of error is the discretization error. So it means that this number n is too small. Because we have to simulate the time evolution operator using a Tokaga function, we have some Tokaga error. And of course, if we use the real hardware, we have some decoherent or incomplete operation. So we, of course, for some errors. So there's, for a long time, there's no knowledge on the computation condition which is suitable to simulate the chemical problem. I mean that like evolution, how to set the evolution time length, or how to set the set number for scheduling function, and so on. So I decided to investigate this point. So first, I tried non-linear scheduling function. So usually we use this blue linear scheduling function given here, but we can use this kind of non-linear scheduling function as well. Actually, this kind of scheduling function has been examined in the AQC, I mean the adiabatic quantum algorithm in this paper. If we calculate a wave function using ASP for this nitrogen molecule in the atom distance 3 angstrom, which roughly speaking the nearly bond dissociation, stable bond dissociation. And if we use the linear wave function, this is a change of the energy, and this is a change of the overlap with the fluid theory. As you can see, there are some differences depending on the scheduling function. Actually, the basic performance can be obtained by using this sinusoidal function because the overlap becomes larger and also converges very fast compared with other approaches. You can see there are some oscillation for this red curve and blue curve correspond to linear and sinusoidal curve. And actually, this oscillation comes from the fact that the derivative at the point 0 is non-zero. So if we use this linear or sinusoidal function, the Hamiltonian changes suddenly at this point from. So this causes some non-diabatic transition to the excited state, which causes some oscillation. But if we use the staging function of 0 gradient at the beginning, we have no oscillation. This is a big difference. But anyway, in this case, the sinusoidal function is better performance. And this is the result by changing the evolution time for nitrogen molecule. If we use the evolution time to be 100, we can obtain very accurate wave function. But if we use t equal 50, the ASP still gives the wave function having the overall less than 0.8. Interestingly, if we calculate the overlap with the ASP with this ASP sum is the ASP wave function obtained from the quantum simulation. And this ASP is the ASP wave function calculated using the psi pi sparse this function. So the difference is that this blue one includes the choker error. The red one has no choker error. The interesting, if we calculate overlap between these two ASP wave functions, the fidelity becomes smaller in the middle of the ASP. But somehow the fidelity recovers. But this trend can be well explained by considering the choker error. So basically, the choker, this is the choker uses the answer is not equivalent to the unchoker uses the answer. So it means that the choker terms operator is not equivalent to the unchoker terms operator. So if we think about adiabatic transition, evolution from the Hardy-Fock state to Sugisaki state, this is the adiabatic evolution path. To adiabatic evolution path. But choke-type adiabatic evolution under choker convention is somewhat different from the original one. So, but the final state should be very close to each other. So this is the reason why we obtain this kind of plot. In the middle of the adiabatic preparation, the difference between two adiabatic paths becomes large. So the fidelity becomes small. But in the end of adiabatic preparation, the adiabatic path for two different cases becomes smaller, which causes some recovery of the choker error. And this is the result of the adiabatic preparation with respect to the evolution time with different molecular geometry. In this case, in the all cases, the sinusoidal scheduling function and the red one gives the best performance. And this is the reason here I can explain the reason why the sinusoidal function is more suitable, because this is the potential energy curve with respect to the scheduling function. I mean the time dependent Hamiltonian. So if the Hardy-Fock is a good approximation, the energy gap between the ground state and the Hardy-Fock state and excited state is larger in the beginning of the adiabatic state preparation. And it becomes smaller if the schedule function become larger. So it means that we can sweep the Hamiltonian first in the beginning of adiabatic revolution. This sinusoidal function so exactly such structure. We can, so in the sinusoidal function, we can change the discrete function value rapidly in the beginning of ASP. So this is the reason why the sinusoidal function gives the best performance. How to set evolution time before performing any Hartree-Fock calculation? What we can obtain from the Hartree-Fock wave function is just the orbital energy. We can use to evaluate, estimate the extracellular energy is the energy gap, the orbital energy gap. So in this slide, I examine the evolution time dependence using this equation. So this red one is the inverse of the homolumo gap, square of the homolumo gap. Purple one also the inverse of the homolumo gap. And this blue one is just a linear inverse of the homolumo gap. As you can see, if we use the purple one, the energy and fidelity is very good, but evolution time becomes very long. So we decided to use this blue one because, of course, if we use blue one, the fidelity becomes worse in the bond dissociation limit. But we already know that we can use the Bloch-Symmetric wave function as an initial wave function of the adiabatic preparation. In fact, using Bloch-Symmetric wave function in the beginning of the ASP, it shows very rapid convergence. So in this case, natural molecule, we can generate this kind of local orbital and generate the Bloch-Symmetric wave function. Unfortunately, this Bloch-Symmetric wave function is not an eigenfunction, so we have some excited state from different spin multiplicities. So in order to use this kind of Bloch-Symmetric wave function as an initial wave function in ASP, we have to introduce this penalty term. So it means that, so roughly speaking, the singlet, triplet, pointing, printed, and septic state have the same, almost the same energy in the absence of this penalty. But if we include this penalty term, the eigenvalue of the extra operator is 0 for spin singlet ground state, but 2 for spin triplet state. So roughly speaking, the spins excited state having different spin quantum number have higher energy in the presence of this extra operator. If we use this kind of extra operator as a penalty term in the ASP, we can obtain the full-scale wave function with much more smaller evolution time. Actually, k equal 20 is always enough. In the case of using Bloch-Symmetric wave function, in this case, using sinusoidal wave function is not good. But this is because in the beginning of ASP, we have some excited state in the vicinity of the ground state. The excited state have different spin quantum number than the ground state. So we have to slowly change the Hamiltonian in the beginning of the ASP. So it means that this DSFD, the gradient should be 0 in the beginning of the ASP. This is very important. This slide roughly compare the ASP with the Hartree-Fock and Bloch-Symmetric wave function. Hartree-Fock is a good approximation for the equilibrium geometry, but not good for bond dissociation. in contrast, the approximate wave function is a good approximation of the bond discussion, really, but not suitable for the equilibrium. But if we use the approximate wave function, the evolution time can be constant. But we need some penalty term. Importantly, the number of Hamiltonian terms can be larger for broken symmetric wave function because, as I said, broken symmetric wave function breaks the spatial symmetry. So it means that if the molecule has some spatial symmetry, the Hamiltonian is block diagonal in the Hartree-Fock space. But if we use the local orbital, such spatial symmetry is breaking down. So the Hamiltonian is no longer a block diagonal. So we have to include some more terms to symmetric time evolution. But still, using broken symmetric wave function is very suitable in the bond association situation. So another problem is how to switch the initial wave function. So we can use the Galactic character because the Galactic character is an indicator of the opposition character. So in this case, I set the threshold to be 0.6. So if the Galactic character is smaller than 0.6, we use the Hartree-Fock space. If the Galactic character is still 0.6, we switch the initial wave function to the broken symmetric wave function. This is nitrogen multiplication. So in this case, we have 1 sigma bond and 2 pi bond. So we have 2 different Galactic characters. But if we switch the wave function using the character, we can set the evolution time like this, and we can obtain the energy and fidelity like this. So by changing the initial wave function from Hartree-Fock to broken symmetric wave function, we can obtain the wave function, I mean the ASP wave function, having the fidelity larger than 0.96. And this is another example for varying the hydrogen molecule in the bond dissociation. In this case, we have only one style character, and we can calculate the ASP wave function. Again, we can obtain the wave function, ASP wave function having the fidelity larger than 0.98. Also, this kind of approach can be applied to some other models. And finally, I will summarize my talk. So in the quant-phase estimation, we have to prepare some sophisticated approximate function having sufficient value overlap with the target energy space. And Hartree-Fock is not wave function is good approximation only for the small molecule and weakly interacting. So strongly correlated system or large molecule, we have to develop some other approach to generate some more accurate wave function. And in this study, we developed 3 different approaches. One is a preparation of symmetric attack wave function, another one is a construction of multi-confluent wave function, and final approach is adiabatic wave preparation technique. And that's all. And thank you very much for your kind attention. I'm very happy to answer your question. Yes. You mean the nitrogen molecule? Yeah. Okay. So I didn't prepare the slide for natural object generation, but anyway, the idea is if we calculate the broken symmetric wave function, this is in this case we have some unequal occupation for spin alpha and spin beta electron. So if we diagonalize the one body density matrix, there are some I can say that there is some overlap between this phi L and phi R, spatial overlap. So roughly speaking, if we diagonalize the one-body density matrix, we can obtain the oscillation number with homo equal to 1. Other oscillation for other order, we have, let's say, 1.9 or something, or 0.1 for unoccupied object. So basically, we can calculate the natural orbital very efficiently by just diagonalizing the natural orbital, adding the one body density matrix. Oh, yeah, so if we use the restriction Hartree-Fock wave function, because the alpha and beta electron occupy the same spatial object. So it means that this Hartree-Fock orbital is already an eigenfunction of the density matrix, giving the, for example, this phi s gives the occultation number 2, phi a occultation number is 0. So using different spatial orbitals for spin alpha and spin beta, it is very important. And of course, we can calculate the natural orbital by using, for instance, like MT2 or CI wave function as well. But in this case, because this is just a Hartree-Fock case, so we don't have to do any Hartree-Fock calculation to obtain the natural orbital. Yes. There are a character. Yeah. So in the bond dissociation limit, we can obtain the oscillation number 1, 1, for instance. But let us think about this wave function. We have 2, 0 and 0, 2 configuration with different questions. So it means that we can obtain, roughly speaking, if we calculate the excitation value of the oscillation number for this wave function, we have 1 minus y over 2 of gravity occupied orbitals, right? So for instance, we focus on this orbital, the oscillation number. The oscillation number can be calculated like 1 minus y over 2 in this case. So roughly speaking, and the weight of this configuration can be changed in the bond dissociation. So in the Vicino equilibrium geometry, the Hartree-Fock is a good approximation. So it means that this configuration have much more larger configuration than this configuration. So roughly speaking, we have y equal to 0. But in the bond dissociation limit, the wave function can be written like this. So these 2, 0 and 2 have the equal probability because in the bond dissociation limit, these two orbitals degenerate. So in this case, in the bond dissociation limit, we have equal question for this term and this term. So it means that we have y equal 1. In this case, the 1 minus 1 over 2 is just 1 over 2 and 1 over 2. And somewhere in between, we have some y in between 0 and 1, and which can be used as a measure of the oppositional character. And this question goes directly related to the occupation number. So we can calculate the directional character from the occupation number. Yes. So basically, if we use the single computational state function, the approximation is good for Bond differentiation, but not so good in the vicinity equivalence. If we use the broken symmetry wave function, the potential curve can be something like, yeah, this one. Because in the broken symmetry calculation, we use this kind of opposite wave determinant as the initial guess. So if this Hardy-Fock state is much more stable than this opposite state, the Hardy-Fock converges to the Hardy-Fock state. So this is the reason why we obtain this kind of potential curve. But still, this broken symmetry wave function is not an eigenfunction of XY object. So if we use the broken symmetry wave function to calculate some property which depends on the spin state depending on some observable using broken symmetry wave function for some troubles, because this is not an eigenfunction of the XY object. Yeah. Which part? Yeah. Okay. This one. I guess. Actually, in the navigator term, usually navigator term means that the discrete function for the navigator term is 0 in the beginning and in the end of the time adiabatic evolution. So the occasion function is becomes something like this. So in this case, I use just include penalty term with respect to ft. So roughly speaking, in the end of the adiabatic expression, the final Hamiltonian also include this extra operator. Yes. So basically, the reason why we include this extra operator is because this wave function is not an eigenfunction. So this broken symmetry wave function is a range on these different spin states. So we have to eliminate unwanted spin states. So this is the reason why I include the penalty function. Importantly, this extra operator commutes to Hamiltonian. So it means that if we obtain the conventional Fluxial wave function without using penalty function, after that we include this extra operator to purify the eigenstates, it doesn't work because Hamiltonian and extra operator commit to each other. But basically, this extra operator has no effect on the singlet state because the eigenvalue of the extra operator is 0. So just this penalty operator just affects to raise the energy for other spin state. So basically, we don't have to eliminate the penalty term in the end of the adiabatic state preparation. Of course, we can eliminate, but not necessary. Yes. Conversion behavior. So I think if we use the navigator navigator operator, it have the conversion in the hardy form reference case. But in this case, I think navigator operator is not necessary because this wave function is a linear combination of the state, and these states have very close, have the energy very close to each other. What we have to do is just eliminate these terms. So this is the reason why I use this kind of time-dependent Hamiltonian. Of course, another reason is the introduction of navigator operator increase the arm. So it means that the increase in the depth. So we want to avoid such increase of the on such depth.